This is Chapter 11, Mountains, Basins, and Continents. Our goals for this chapter include an investigation of factors that control elevation. Uh, Additionally, we'll look at how mountains and basins form. We'll investigate characteristics and origins of terrains. And we will look at how continents grow. Not unlike the seafloor chapter, we'll look at the positions of continents over time. Okay, so this is the region around the Tibetan Plateau in southern Asia. This is the largest, highest, flattest plateau on Earth. We have an exaggerated topographic profile of the region at the bottom here. The Tarim Basin is 3,000 meters lower than the elevation of the plateau. The Himalayas rise along the southern edge of the Tibetan Plateau. Mount Everest is the world's highest mountain. It's 8,850 meters above sea level. India to the south has much lower elevation and relief. Okay, so we have Mount Everest and a view of the Tibetan Plateau and Himalaya. So let's think generally about regional elevation. Regions with thick crust are generally higher than regions with thinner crust. Regions that are underlain by less dense crust are higher than more dense crust. And then regions with warm rocks are less dense. Those rocks are less dense. So warm regions are higher than cooler regions. And you can see that in the block diagram here. So what are some ways you can decrease regional elevation? Well, through faulting, you can structurally thin crust. We have a normal fault here and then regional subsidence happening. Thicker crust and then thinner crust. You can decrease elevation through erosion, like the Appalachians in North America have eroded quite a bit over time, and they lost elevation that way. You can cool that crust or mantle, and then that'll result in subsidence. So to increase regional elevation, you can shorten or thicken the crust through a thrust fault. You could add surface material, like through a volcanic eruption, and it heats up the crust too, so that'll add elevation. You can add magma from beneath with an intrusion, and we'll see rocks expanding because of that. If you simply heat the crust or mantle, you have less dense material now with heat, and elevation should rise. Okay. So the tectonic setting of regional mountain belts. We see these often at subduction zones. Convergent margins are high because the crust is thickened by magmatic additions and crustal shortening. So regional mountain belts also occur in like continental collisions. Those are high due to increasing crustal thickness as one continent is shoved beneath another. And then with mantle upwelling, a dense mantle can be heated by or replaced by upwelling of a less dense asthenosphere. We'll look here at the location of regions that have high elevations and think about why they're high in elevation. All right, so Western North America, it's been a convergent margin for most of the last 200 million years. So you have magmatic additions and colliding island arcs and pieces of continents adding to the elevation. The Alps have thick crust due to collisions between Europe and smaller continental blocks. The Zagros Mountains, you have there the collision of the Arabian Peninsula with Eurasia. The Tibetan Plateau, of course, has the collision of the Indian continental fragment with Asia. The Andes are located above a subduction zone, so you have this thickness due to magmatic additions and crustal shortening. And then the East African Rift, that has magmatic heating and the presence of a hot spot there, which causes the area to rise. Lastly, the Great Divide Range. There's no plate boundary here. So there's some questions as to why it is so high in elevation there. Apparently there's debate on the age of the uplift and origin, so I don't have a lot to say about that. So what happens as mountain belts erode? I mentioned the Appalachians in North America have had significant erosion. Let's start with early mountain building. As a mountain belt forms, the uplift is usually faster than erosion. All right, to get the mountain itself. And then as soon as the mountain forms, it will be eroded, which contributes sediment to low areas. And then there's something called isostatic rebound. So as material is eroded from a mountain, the crustal root drives the uplift, like so. We call that isostatic rebound. And then sediment from the mountain is deposited in nearby basins. It adds weight and it depresses the crust. And then erosion and uplift can bring deep rocks to the surface. Deep rocks are exposed at the surface, then especially metamorphic and plutonic rocks. The mountain is then eroded down and the crustal root is gradually reduced in size. And the material eroded from the mountain, of course, ends up in adjacent basins. It's a source of sediment, and then it increases the thickness of those basins. So what might control the elevation of North America? We have a wonderful cross-section here from the west coast to the east coast. So if it's America, we say it's from sea to shining sea, right? Here we have it. Western North America, it's high in elevation because, of course, it was a convergent margin. The Rocky Mountains were thickened by deformation within the plate. Okay. And the Great Plains have a marked decrease in elevation because the lithosphere is cooler and thicker than it is further west. And then the Appalachian Mountains have much thicker crust, higher elevation due to the collision between North America and Africa long ago. And like I said, they've had a lot of time to erode. We can zoom in on those as well. All right, so faulting can result in the formation of mountains. Here's a thrust fault. If the overthrust block is uplifted faster than it is eroded, then we get a nice little mountain. We see that in Colorado's Front Range or the Rocky Mountain Front in Montana. You can also get mountains forming through normal faulting and extension. So one block is going to slip down, forming a basin. The other block remains high, forming a local mountain. And here's the basin near Death Valley. So how can folding form mountains? Folding in a tectonically active area can warp the Earth's surface as well as the underlying rocks. This cross-section shows a thrust fault beneath Los Angeles. And we see in the photograph, this is Dinosaur National Park in Utah and Wyoming. We have erosion of previously folded rock layers, and we can see that this is why the area was so high here. These rocks are cut, and you see in cross-section really what happened. Differential erosion can also form mountains. So what does that mean? You can have a hard rock layer in a sequence of rocks that resists erosion. And those resistant rocks protect the underlying softer rocks beneath from erosion, forming a local hill or mountain with steep sides like this mesa in Moab, Utah. Also, a granite pluton can resist erosion, so you get erosion all around it, and that area becomes a high point relative to everywhere else. An example of that would be Stone Mountain in Georgia. You can also see these tilted resistant layers sticking out as little mountain structures with erosion over time. So where do basins form? Here's a few different settings. You can see them in passive margins. Rifting can form passive margins that has thinned the crust and formed basins as well. Continental rift. Here you have extension of continents, commonly producing rifts or grabens. And then normal faulting can downdrop a block, giving you the space for a basin to form. Oops, one back. A foreland basin as well forms where crust is warped by the weight of thrust sheets, and a depression forms in front of the thrusts. And then with strike slip faulting, motion along the fault, especially near bends on the fault, can downdrop one block relative to another. Or you could just have regional subsidence, where you have broad regions that might drop in elevation due to cooling or movement of the underlying mantle. And here's the major basins that we have in the lower 48. Note the Michigan Basin, the Illinois Basin, those formed within the continent, probably due to Paleozoic collisional tectonics in the Appalachians. So kind of the eastern extent of what happened with the Appalachians, believe it or not. We'll zoom in on the Michigan Basin. So here you have sedimentary rocks that were deposited during the early and middle Paleozoic. It shows you kind of a bullseye pattern on a geologic map because the rocks dip in towards the center of the basin. And I regret that the full upper peninsula is not shown here. The youngest layers, the blues and the greens, are in the center of the basin. Well, browns too. It probably formed during an episode of continental rifting, but with all the sediment that was in it, it probably kept subsiding to form what we see now. Okay, so processes that form basins and mountains at convergent boundaries. You can have an oceanic trench forming and acting as a deep basin that traps sediment. And then you get an accretionary prism. Of course, this is under ocean-continent convergence. That's a complex zone of faults and folds along the upper parts of the subduction zone. Behind it would be a magmatic arc, and that magma rises into and thickens the crust. And then behind it, you could get a fold and thrust fault belt, really, of those things behind that arc. And the weight of the thrust sheets flexes the continent downward, forming a foreland basin in front of the thrust belt. If it's simply just continental collisions, you have one continental plate shoved beneath another, forming a foreland basin in front of the collision zone. And the collisions form folded and faulted mountain belts with thrust faults that thicken the crust. The uplift and erosion bring metamorphic and intrusive igneous rocks to the surface. But behind the collision zone, rocks are folded and thrust away from the mountain belt. Any crust that's too thick or hot begins to spread under its own weight, forming normal faults and basins. And then stress associated with the collision can cause tectonic features to form many kilometers away from the actual plate boundary. Okay, let's talk about extension on non-rotating fault blocks. So in this case, you have normal faults dipping in opposite directions. Now, with extension, the upthrown blocks become mountains bounded by faults. And then erosion of those mountains contributes sediments to basins. Those mountains are gradually eroded, and the basin sediments may overlap the edges of the range. With extension on rotating fault blocks, normal faults might dip in all in the same direction. During movement, the block and faults rotate. The corner of the block rotated down becomes a basin, and the corner rotated up becomes a mountain or a ridge. And those can have kilometers of displacement. So continued faulting tilts the units more, extending the crust. And we see that, I think I've got that in Death Valley, California. Okay, so when extension accompanies subduction. Now, extension can occur in front of the arc, causing the thrust to thin. We see extension here. Extension can occur within or behind the arc as well, where the crust is hot and weak, producing normal faults that thin the crust. If extension continues, the arc can rift apart and form a new ocean basin. So a back arc basin can be formed by back arc spreading. We've talked a lot about hot spots, and we'll focus in on continental hot spots. Okay, so up top you have the Afar region in East Africa. The hot spot there is interpreted beneath that region, right? And near the hot spot, the Arabian Peninsula has pulled away from Africa along the Red Sea and the Gulf of Aden. The Red Sea, the Gulf of Aden, and the East African Rift come together in the Afar region. And the East African Rift might never be large enough to be an ocean basin. All right, and here we have Montana, Idaho, Wyoming, the Yellowstone region. So the region around Yellowstone National Park, it's higher in elevation than surrounding areas. So think about what we know about how magma can make an area higher in elevation. Now, Yellowstone has had 3 huge eruptions in the last 2.1 million years. You have heat from volcanic rocks and magma producing those hot springs and geysers. Yellowstone is interpreted to be the location of a hot spot with the caldera, and the Snake River Plain records the track of North America over the hot spot. Okay, so how do continental hotspots evolve? A solid mass rises from the lower mantle and melts. You get a broad dome uplift with 3 arms. Some of the magma escapes to the surface, and you get normal faults with extension forming basins. Rifting along, say, 2 arms forms a new ocean or can, and then a 3rd arm could fail to break up a continent as well. And out of view, you would then see seafloor spreading continue. That's how it might evolve over time. Okay, continental interiors. You can have something called a continental shield. We have it in Canada. It's composed of old, metamorphic, and igneous rocks. We can also call those crystalline basement rocks, generally in a central region of a continent. You can have Continental platform, I'll highlight that here, characterized by nearly horizontal sedimentary rocks deposited on top of the basement rocks and containing, and like they're on top of the broad basins and uplifts, I would say. So you could also have a boundary between the platform sediments and the basement, and you could think of that as a major unconformity separating rocks with different ages, structural geometries, and geologic histories, as we talk about in Chapter 9. An example of this could be seen across Ohio. You have Paleozoic sedimentary layers dipping gently off the flanks of a dome. And then igneous and metamorphic rocks of the basement rest beneath sedimentary layers, but they're not exposed in the area. So what sort of processes affect continental interiors? Well, you can have stresses from far-off plate boundaries and other tectonic activity causing uplifts in basins. You can also have faults, folds, domes, and basins. And some people are interested in this for, say, a final project. Global climate change or other processes can cause sea level to rise and fall, and that will affect what is really interior to the continent or not. Or maybe it'll all be submerged again. Let's think about tectonic terrains. And what are those? That's where you have a bunch of different types of rocks sort of squished together, and they are bounded by faults and shear zones typically. You see the boundaries in black. So adjacent tectonic terrains have different sequences of rocks, ages of rocks, and types of structures. And then adjacent terrains can have different fossils, rock chemistry, and metamorphic and igneous histories. And those terrains generally form in different tectonic settings. Alaska is our great sort of nearby example for a continent that's just a bunch of terrains squished together. So thinking about that, common settings for the origin of terrains. Got a piece of the seafloor here. Some terrains contain pillow basalt, deep sea sediment, and other attributes that indicate it originated as oceanic crust. You could have another thing that would later be found in the terrain being an oceanic island or plateau from a hot spot. So this would be thicker and less likely to subduct, more likely to be added to the edge of a continent. We call that accretion. An island arc could be another terrain component. A piece of a continent, why not? With thick granitic crust, continental sediment, actually. And then an accretionary prism. So we could add them together, accrete them via subduction, collision, or strike-slip faulting. And I mentioned Alaska. This is what we see. The gray areas are the considered to be the stable North American continent. And then there's Alaska. It's composed of numerous terrains. This area in red is interpreted to have originated as one or more island arcs during the late Paleozoic and early Mesozoic. The blue areas are parts of North America sliced off and transported. The purple and green areas, those are slices of oceanic crust and accretionary prisms. And then the pink and red, again, island arcs or magmatic belts. The yellow areas are more recent rocks and sediment that overlap terrains. So that is extremely cool. That's why Alaska is cool, for so many reasons. All right. So this geologic map of North America, I have it on my office wall. This is a good one, right? So the oldest rocks here are exposed in the Northwest Territories of Canada, 4 billion-year-old Acasta gneiss. The eastern half of Canada is the Canadian Shield. The Southwest and Southern Rockies are added to the southern edge of North America between 1.9 and 1.6 billion years ago. Should probably be highlighting this. So Precambrian, dark brown, red. Paleozoic, purple and blue. Mesozoic, green. Cenozoic, youngest, yellow and tan. Okay. And these Paleozoic and Mesozoic green sedimentary rocks overlay the Precambrian basement rocks. So we go from much older. These are the first things exposed. If you were to dig through a bunch of soil in some places, you'd encounter these old rocks first, to Paleozoic, to Mesozoic, and Cenozoic. And we'll look kind of to close this out at a geologic map of the world, noting the distribution of rock ages. So our oldest rocks being on the bottom of the legend here, and then youngest, kind of yellow Cenozoic. Northern Europe contains the Precambrian Shield. Eastern and Southern Europe were added in the Paleozoic, Mesozoic, or Cenozoic. Most of Asia was assembled from terrains during the Paleozoic and Mesozoic, and Western Australia's got some really old rocks in the Precambrian. Eastern Australia was not sort of formed until the Paleozoic. India has a lot of Precambrian rocks, which were once part of Gondwana, and rifting broke up that shield. Africa has several Precambrian shields, which collided in the late Precambrian and the start of the Paleozoic. And the oldest regions in South America are on the eastern side and were once continuous with rocks in Africa. The western half was constructed more recently during the Paleozoic and Mesozoic. So just to give you an appreciation for this and a perspective for the distribution of rock ages throughout the planet. And we will stop here for today.